quiz that you had on Thursday was mostly graded by Mr. Aliotto again. I graded a couple or three with him. But the grades were pretty good. The average for the 22 papers handed in was 91.6. So it's, I don't know whether he's particularly a lenient grader or whether this reflects the fact that you studied very well and understand this material pretty well. I was going to, well, are there any questions about the problem on this graphical method of determining ideal stages, or on the quiz? The problem on the quiz, of course, was the type that is not very realistic as far as concentrations are concerned, but nevertheless gave you a chance to demonstrate that you understand the principle. Now, there's one of the points about this that may be a little bit confusing, and that is you could argue with me about one plus or minus one ideal stage at times, because if I ask you how many ideal stages are required, that is really one stage more than the number of ideal trays, because the pot is a stage. And perhaps if we made a little sketch here again of a hypothetical situation, we might visualize this better. Because in fact, in several textbooks, you'll find examples of these kind of problems worked out, and they'll determine the number of ideal stages, and then they'll say the number of trays is 1 minus. Take off 1 for the still pot. Because let's say we have a simple case here of a K-Mathili diagram where this is the curve, equilibrium curve. Can't seem to get out of that. And we have some x of d here and an operating line like so, and here's the intersection. And then this would be the operating line, let's say, for the stripping section, x of b. Using live steam, the way I've drawn this clear down the diagonal. And so if these lines represent the operating lines, and this x of b, of course, this represents the composition of liquid in the still pot, or in other words, the liquid at the base. And so the vapor in equilibrium with that would be that obtained by projecting vertically up to the curve. So if you call that stage 1, that really is the pot. So I prefer to write that as having the composition x sub 0, y sub 0. And then if you take the step over here, this point here, of course, is x1, y sub 0. In other words, this is on the operating line is the composition of the liquid on the first tray above the pot, and the vapor that's arising and interacting from that from the still pot. And of course, numerically, this y sub 0 is the same as that if you project it horizontally. This x and y. And projecting up here, then this would represent x1, y1, and so forth. And so then this would be tray 2, 3, 4, 5, as I've drawn it here. Ideal trays. It'd be 6 stages if you count the pot. Now also, the way I've crudely drawn this, you might consider here also that here on this 5th tray, which of course this represents, the point on the curve represents x5, y5, that this is gives distillate which is slightly more than the requirement, slightly more than x sub d as I've drawn it here. So in reality, you need slightly less, or in other words, you need about 4 complete ideal trays, plus maybe about 4.8, plus about 8/10 of another one. So actually, this solution here, as I've drawn it, you need about 4.8 ideal trays, plus 1 for the still pot, or maybe 5.8 total stages. Well, this may seem like a rather minor point, but it is sometimes confusing a little bit on whether we're talking about trays or stages. Is that clear? Do you understand what I've said now? And of course, sometimes it's equally correct to start the steps from the top and go down the other way. And in that case, if I had drawn it in a comparable fashion, this last step here would have gone down slightly below x sub b, so it's showing again that the 5th real stage was slightly more than required. Of course, in real practical problems where you're dealing with separations into essentially pure components, at least in the even case of alcohol, where you're trying to get essentially water as the bottom's product, why we're really dealing in terms of 20 or 30, 40 maybe ideal trays in a practical problem. So arguing about 1 or 2 or a fraction of 1 is quite academic. Question?
Yep. As we know the feed conditions, why don't we start counting from where the feed's introduced? We know that's going to be on the tray.
Well, that's okay. That's perfectly all right, and it should come out to be the same. To be kind of rigorous about it, you'd have 2 fractions at either end, 2 fractional stages at either end add up then. Most likely it'd come out that way, or in other words, the step wouldn't coincide exactly with the specified bottoms composition, the distillate composition. It'd be a fraction of a tray, but it should be exactly the same number of steps if you draw it accurately. Well, I'd like to, well, before I introduce something slightly different here, I'd like to say that I want to give you another exercise, but which is somewhat difficult, but we'll work it out in class. Today, however, I'm going to hand out, if I can find it here, the problem, the requirement, so you can look it over. What do I do with those? Somebody conceal them from me. No, here they are. Here they are. I conceal them. I conceal them for myself. I know you're anxious to get it. So here's an exercise I worked out a few years ago in which it requires some new concepts or new things that will give us an opportunity to bring up, such as plate spacing, fusel oil decanter location, and height and diameter of column, treated in a rather elementary sense, but nevertheless to illustrate some of the points. Now, as I hand this out, there's just one change that you might make on this, and that is under, well, first of all, you can call it problem 6 instead of problem 8. I think it's problem 6 of our series. And under requirements, under A, where it says feed rate 15,000 gallons per hour, 7% alcohol by volume, preheat 180 degrees Fahrenheit. 140, I mean, degrees Fahrenheit. And that part in parentheses assume the specific gravity and specific heat are the same as for water. Well, just delete that. We're not going to make that assumption. So this is to illustrate here the fact that we got a situation where we have two products, distillates. In other words, we have a heads from the condenser, and then we have a side stream product. So we have two operating lines, or the operating lines change as you come down from the condenser down to the point of the side stream, and then it decreases in slope. But I won't take time to go into that now because the approved solution, as we call it, that I'll hand out tomorrow will illustrate it. How you calculate the slope, or the change in slope, or at the point where you take the side stream out. It's quite simple. So look that over, and maybe you might even consider how you'd approach the problem. But I will hand out a solution and go through it with you. Now, I'd like to take a little time to discuss the question of feed tray location and the result of using an existing distilling column in such a fashion as whereby you introduce the feed at a tray which is does not have the composition of the feed. Let me say that again. I want to consider the condition which results in the situation where the feed composition is being introduced onto a tray in which the liquid on that tray, or the overflow from the tray above down to that tray, is different, significantly different, which results in sort of a reverse action of which you're defeating the purpose of separation or concentration by mixing a stream of one composition with that of a different composition, defeating the purpose of fractional distillation, which is, of course, is to separate stepwise one component from another. Perhaps we can visualize it a little bit better by attempting to draw a little sketch here, not significantly different than the one I just erased here, but suppose we have a particular situation, again represented by a diagram of forgot to bring a straight edge this morning, which helps. And here's an equilibrium curve. And let's say this this value here represents x sub f, and somewhere here we've got x sub d, and maybe this is the Q line with a little slope here. So we have an operating line here with determined by the reflux ratio, which has a slope which is something like that. Now I'm going to project this a little beyond with a normal point of intersection with the operating line of the stripping section. Let's say if this is x sub b with open steam, we'd have an operating line for the stripping section that would come down to this point here. All right, now then, ideally, and starting from the top in this case, for convenience, we'd have about this many steps here. 1, 2, 3, before we'd cross over to the operating line for the stripping section. But in reality, we're operating a system which, in effect, has, let's say it has about 7 ideal trays in actual operation. Well, if those trays are there existing, they're going to be functioning. There's going to be vapor-liquid interaction on those real trays, and there's going to be a certain amount of separation occur. And so you represent this on the diagram by continuing the steps until you've used up all the trays that you have. Something like that. In other words, here's 3, 4, 5, 6, 7. Finally, after you've used up your last ideal tray, which I've arbitrarily assumed 7 ideal trays existing, but only 3 ideal trays required. Well, and finally, after we've used up the 7th tray, well, then we drop down to the operating line for the stripping section, for the next step, and so forth. So you see what's happened is that the overflow from the tray 7, which is the tray number 7 then, would be the tray immediately above the feed, as I've drawn it here. Tray 7 is immediately above the feed. So that we have the overflow from tray number 7 that's considerably lower than the feed. The feed's over here, this value. And you can notice also that in a situation like that, the steps have become very small. Very little change in concentration is taking place. We call this a pinch situation, or a series of pinch trays, because the conditions of the graphical solution to the McCabe-Thiele equations requires to be represented as I have here. So in other words, what we have in here is a pinch region, as they frequently call it, pinch region immediately above the feed tray. Or sometimes it's called an inactive tray region because there's practically no change in concentration over several trays in here, let's say, or inactive tray area. Do you understand what I've tried to say here, illustrate? This is a condition that's very frequently met with, and as distilling columns are used here in California for distilling, particularly when they're making beverage brandy, as we saw down at the Bear Creek Winery, where they were just drawing off side stream at 170 proof. I don't remember now how many trays above the feed, but they had some 42 trays in that fractionating column, in the rectifying section of that still. And so, I'm sure if samples were taken on the trays below the draw-off, which probably the draw-off of the side stream product was somewhere around 20 or maybe in the middle somewhere, which is all right. It's not a bad way to operate it once you've got 40 trays there. But if you had taken samples of those trays immediately above the feed, you would have found them very low in alcohol, much lower than 10% alcohol, the composition of the wine, 11% alcohol. Well, what happens is that, of course, it gives you, with a fixed number of trays in the stripping section, it gives you somewhat greater effectiveness of stripping. Let me illustrate this in a more general way by drawing another little sketch here in which we plot the composition of the liquid versus tray number, or stage number, whichever you want to call it. And this would represent the bottom, and this would be the top tray. And let's say this represents from 0 to 100%. And some value here we have the feed composition of the feed. All right, now somewhere along in here we have the actual feed tray. This is the feed tray. And this, counting from the bottom, this would be 1, 2, 3, 4, 5, 6, 7, 8, and all the way to the top. This would be the top numbered tray. These are actual tray numbers. Now, if we have, if we're operating a column in the ideal manner, in which the feed liquid on the feed tray is the same as the feed composition entering on the tray, we will have a distribution of alcohol or the volatile component from bottom to top. That will have some value that'll look sort of like this. It'll be a sort of a sigmoid shape, because we get the maximum change in concentration in the middle part of the column, where the curve is farther from the diagonal. And so this would represent, and I'm going to label this curve number 1, because I'm going to draw a couple other on there. So for this situation, this would be the composition of the bottoms, X of B1, and this would be the distillate, X of D1. So this represents more or less the ideal situation, which we get the maximum separation for a given number of trays. This is the actual number of trays. We can call it ideal trays, or it doesn't make any difference. It could be actual trays as far as the purpose here is concerned. Now, if we, so in other words, this would be the case where the feed tray has the same, or the overflow from the tray above mixing with the feed is exactly the same composition. Now, if we translate the situation that I attempted to demonstrate here by this little sketch to this kind of a presentation, we'll find that we get this sort of a situation. The composition of the bottoms will be somewhat less, because you have a fixed number of trays in here in the stripping section. And a fixed number of trays in the rectifying section, the concentrating section. And since the overflow here from the tray immediately above the feed is considerably lower than it would have been if you are introducing than had we been using the ideal situation where it's introduced there. It's obvious that a fixed number of steps here is going to lower the bottom's concentration to somewhat lower than it would be under the original design situation. So we'll have some value like this, and the distribution curve will look something like this. But here you'll have this inactive tray area, and then it'll finally break off and go on up to some value like so. This is case number 2, where X of B2 is less than what you would have gotten under the ideal situation, ideal application of the of it. And then you have this region of trays here, which we call the inactive area, inactive region. From about there to there. Correspondingly, it comes out to be that X sub D2 is somewhat less than our original specified or distillate concentration. So in other words, you could say it another way, that when you operate a column this way, you get an inactive region above the feed tray, but it will result in somewhat better stripping of the volatile component out of it, but it'll result in a lower product quality, at least a lower product concentration, than it would be possible under the ideal situation. Or the ideal situation would be that in which presumably the existing column was originally designed. Then we can have the reverse situation where the concentration of alcohol or the volatile component on the feed tray is somewhat larger than the feed. Again, we're getting an inverse action somewhere in the column because we're mixing streams of two different concentrations. We're getting an inverse effect of what we're trying to do is separate. And then what it amounts to is that you get an inactive region down below here. You'll get a poorer stripping, and you'll get a inactive tray region here, and then it'll finally go up here and get a slightly higher product concentration. So this would be X sub D2, where 2 corresponds to this, 3 I mean, where this corresponds to curve 3. And this here would be X sub B3. So in other words, to summarize this, you'd have for curve 1, you have the feed composition is equal to the composition of the overflow from the concentrating section. That is overflow from the last tray of the concentrating section onto the feed tray. Curve 2 represents the feed composition is greater than the composition of the overflow from the concentrating section. And curve 3 represents the situation where the feed concentration is less than the composition of the overflow from the concentrating section. And so the result is, for case 1, the results are, for case 1, we have a X sub B and X sub D are as specified or consistent with the original design. Situation 2, we have an inactive tray area, series of pinch steps, above the feed tray. And also somewhat better stripping, if you want to put it that way, say improved stripping but lower product quality or lower product concentration. And case 3 results in an inactive tray area below a series of pinch steps below the feed tray. And less effective or incomplete stripping. But a somewhat higher product quality or higher product concentration. It reminds me of one of the first times I was asked to consult with a member of the industry was first year I was here, and a fellow came in with a set of data they'd taken from their distilling column, and the data consisted of the composition of the plates from the various trays of their distilling column. And in fact, this was the same data was published in an article in Wines and Vines in 1939, and was one of the first reports in the literature, at least in the United States, of tray concentrations and typical distilling concentration. So he asked me to look at it, see what I thought of it, and it was this situation that I've indicated here, in which there were about 10 trays or more in this particular case, which the tray samples were lower than the feed, and I pointed that out to him. He hadn't even realized it yet, and didn't know that that's what it, hadn't realized that's what was the situation, and was quite surprised. But this is the way a lot of the columns are operated, and intentionally so, or deliberately so, by the industry, because many of the columns we have were designed to produce a very high product concentration in order to produce essentially wine spirit. In other words, most all the columns existing in California were always purchased with the capability or the intent of being able to distill 198 or 192 proof spirit. If you have 40 trays in the concentrating section, you don't have too much difficulty getting up to 192 proof. The top of the column, maybe 193 even, is not uncommon. So if you apply those to a production of beverage brandy, which the distillate concentration is only 85% by volume, and which, as the examples we've had, I think, indicate that you only take 2 or 3 ideal stages, or 4 at the most, to reach this concentration. The rest of the trays, even allowing for a reasonable plate inefficiency, are considerably more than required. Now, this is what I've stated now. What I've just stated is from the viewpoint of concentrating alcohol. There are some other reasons, however, in which there's some advantage to having more trays than you need, and that is in the treatment of or separation of the volatile constituents. For example, the heads components, the acetaldehyde and ethyl acetate and diethyl acetal, if you have some SO2 present, which causes the alcohol and the aldehydes to react to form acetal. This means then that you have, with a goodly number of trays, much more than you need, you can have a situation where you draw the product off at, let's say, 85% by volume, and the heads would be 192 proof. You've got a good number of trays to concentrate the heads. For example, the Bear Creek Winery, let's say they had, as I think they said, they had 42 trays, and so they're probably taking the brandy off. I didn't fail to count it the other day when we were down there, at maybe 15th tray or possibly the 20th. So you got about 20 trays to concentrate aldehydes in that situation. What is the disadvantage of using this kind of a system? Well, the only thing is that you've got more metal there and more equipment than originally was required. May cost more. If you put in a still like that just to produce beverage brandy, you normally wouldn't put in that many trays. But once you have it, you get a better separation of the low volatile constituents into the heads cut, and the cost of operating is very little more than it would be for a smaller column or a shorter column. It'd be a little bit more because you have more metal exposed, so you get some heat losses to the surroundings and so on. And another point in connection with this is that many of the stripping sections that are used in California are not highly efficient in the sense that they're sieve trays and they're operated in such a way that with a very high load rate that they probably only get a plate efficiency of 40% or something like that, 40 or 50%. So the operators have found in practice that by operating the rectifying section in such a way as I've indicated here, so that you have some inactive trays above the feed, that they're able to get the stripping down to the desired value by operating it in this fashion. I've seen many operators even producing high proof spirit, getting only 188 or 189 proof at the top, the draw-off point near the top, with 35 to 40 trays, and when they could easily have attained 192 proof by changing the operating conditions so that the feed concentration, so that the feed tray liquid was nearer to that of the feed. Well, now then, this problem we're going to work out tomorrow has to do with a little bit about plate spacing. Another parameter that I mentioned initially is, are there any questions about this before we erase it?
You said that if you had low plate efficiency and you had an inactive region above your feed tray, that was good. That's what they wanted, that, so they got better concentrating?
Well, maybe I didn't say it very clearly, but what I said is that many of the times our stripping sections are relatively low efficiency as far as plates are concerned, so that if they have 20 trays, they only have maybe 10 ideal trays, and although this will get you down to a pretty low level if you try to plot it on a curve like we have, when you try to get down to as low as 2 to 3 or 4 hundredths of a percent alcohol by volume, it takes a lot of steps right down at near the bottom to get it down to that low value. It should be obvious now that if you're trying to approach zero alcohol as a limit, it'll take an infinite number of steps, because the very nature of distilling columns is that you cannot get every molecule of alcohol out of the liquid, out of the feed. You approach zero alcohol or zero concentration of the volatile component as a limit with infinite number of steps. So it all depends on what your tolerance is for allowable loss. You'll find many operators will tell you they have zero loss in the stillage. Well, by their method of testing, that may be what they find. But in reality, there's always some there. They haven't used a sensitive method of measurement. To get allowable loss of the order of 200% by alcohol by volume is about the limit that can be attained with any of our equipment. 0.05 is probably more typical of the losses that are the concentration of alcohol in the bottoms. This brings up another thought that I have, which is a little bit divergent from the purpose here, but that is the effect of the concentration of alcohol in the feed. When we're recovering alcohol from waste material, residue material, such as wash, pumice wash, and so forth, there's a tendency in industry to use a lot of water in order to get more complete recovery of the alcohol, with the result that sometimes the alcohol concentration of the distilling material may be as little as 2% by volume, sometimes less than 2%. Now, if you're compared the situation of, let's say if you had a feed of 2%, you might get the alcohol stripped out to 0.02, let's say. I better not try to work out an example because I don't have it here, but let's say you might get it down to 0.02. If you were able to operate your plant in such a way that your distilling material was 5 or 6% alcohol by volume, and maybe the stripping you get it down to 0.04. Well, if you stop and figure out the recovery, you've got much higher recovery of alcohol by using the high alcohol feed, even though your allowable loss is slightly more, or twice as much, than for the very low alcohol feed, where you get a slightly lower stripping, lower alcohol content of the stillage, but the percent recovery is considerably low. Maybe next time I'll work out a little example there, but you could do it yourself. Assume a feed rate of 15,000 gallons per hour, like this problem we're going to work on here, and and consider what it would be if you only had 2% alcohol instead of 7% alcohol for the same number of trays. Now, the question of plate spacing, in its simplest consideration, is very simple. But there are engineers go into considerable empirical type treatments in order to determine this. But anyway, plate spacing would be is determined by, or has to be taken into consideration, arrived at by taking into two parameters into consideration. The first is vapor handling capacity, and secondly, the liquid handling capacity. Now, as far as the vapor handling capacity is concerned, I'm not going to take time to go into the mathematical treatment of this, although there is in the textbooks considerable mathematical treatment of how you arrive at a proper plate spacing. But in reality, it's quite empirical treatment. It's not very much. And it's still subject to some controversy as to how accurate the data is. But nevertheless, let's consider under vapor handling capacity we have the question of the parameters that affect the plate efficiency. Vapor handling is related to plate efficiency. some of the factors here that enter into this, without trying to relate them in any way, are vapor velocity. And liquid entrainment. In other words, if you have, for a given plate spacing, the bubbling action of the liquid on the tray causes a certain amount of droplets to be thrown into the air, and if you have sufficient vapor velocity, a greater percentage of those droplets will be mechanically entrained with the vapor and onto the next tray above. And of course, this is obviously defeating the purpose of distillation, because you're mixing again two concentrations of liquid phases that are different. The concentration of the liquid on the tray below is lower than that above. So if you mix them by entrainment, well, you're defeating the purpose of distillation, the progressive separation, or progressive change in concentration from tray to tray. And so from the standpoint of, and this considerably affects plate efficiency, see how much entrainment takes place. Also, in that consideration, there is a certain degree or optimum range of bubbling action on the tray, so if you have too low a vapor velocity and maybe have no entrainment, negative entrainment, but you don't have very much action on the tray, you don't have complete interaction of the bubbling and with the liquid, you'll also get low tray efficiency. So there is a region there of maybe a fairly wide range, but a region in which you get better efficiency due at higher rates or lower rates. Vapor rates I'm talking about. So in other words, there is a sort of a range of allowable vapor velocities consistent with particular plate spacings, and they range from about 2 feet per second, maybe up to 5 or 6 in practical applications in the alcohol industries, maybe higher than that in some chemical industries or petroleum refineries. But 2 to 4 feet per second would be the range of vapor velocities utilized in the alcohol industry, as far as I can figure out or learn. And perhaps I'll give you a table at a later period, which I worked out one time, which indicated that from the standpoint of suitable plate efficiency, that you ought to have a plate spacing of at least 10 inches for a vapor velocity of about 2 feet per second. So nowadays we recommend that trays be put no closer than 10 inches apart. If you want to go up to 12 or 14 inches of plate spacing, maybe you can get up to 4 feet per second, something of that order of magnitude. Now, from the liquid handling viewpoint, let's see. Well, I guess our time's up. I'll take that up next time. But in effect, from the liquid handling capacity, you have to have enough plate spacing so that the pressure drop across the tray is not sufficient to back the liquid up in the downcomer so it floods the tray above. And so as a general rule, they try to estimate the pressure drop across the tray and allow a plate spacing which is at least 2 times the liquid height in the downcomer for normal conditions, to give about a 50% leeway. Okay, well, that'll be all for this morning then.